And we are joined by Madjid Mohseni, Scientific Director at Rizal Center for Mobilizing Innovation at the University of British Columbia. And we are going to talk about research with the Water Quality Research Foundation, one of the projects going on there. So, Madjid, thanks for joining us on WQA Radio.
Thank you for having me.
Let's talk about the role you play at the University of British Columbia, scientific director, and the center, I should say, the Center for Mobilizing Innovation. What's that all about?
Yeah, I am a professor here at the University of British Columbia, and my role here is to do both teaching and also research. As you pointed out, my research is around water quality and treatment, particularly focusing on drinking water quality. And I am also the scientific director of Rizal Center for Mobilizing Innovation, which is a national program funded by Government of Canada and a range of partner organizations from industry to some NGOs and also other government agencies. And the focus of this program is really to bring technologies and innovation from university labs and also what might reside outside university labs into the communities to develop those technologies, to implement them, and address the water, drinking water quality in communities outside the urban area. So the specific focus we have are around more rural and remote communities that do not have resources to have high-end or advanced water treatment systems and are often relying on, in many cases, decentralized treatment system, meaning that at home, whether it's a point of use or point of entry water treatment systems. And that's how it also very relevant to the mandate of water quality associations, which are individual treatment systems.
What are you focused on these days? Any particular application or treatment process?
Well, there are two aspects that we focus on in our research. One is around ensuring that the drinking water is free of pathogens or microbes and bacteria. And those are very key because those are the primary threat to public health. The second focus is around what we call emerging contaminants, micropollutants, whether they are pesticides or cyanotoxins that come from algal blooms. And in this case, that is relevant to the Water Quality Research Foundation research is PFAS, or per- and polyfluoroalkyl substances.
Before we jump into that a little bit more, let me go back to something you said about the rural residents that you're primarily focused on. How many people in Canada would you say are in this decentralized situation?
Well, in general, it's estimated that roughly about 20% of the population live outside the main major urban areas. So we're talking about roughly around 6 to 8 million people. Now, not all of them are connected or relying on decentralized treatment systems, but a large portion of them, they are. Many cottages and cabins and basically a spread out communities. They rely on single wells and single treatment systems. But also on top of these 20%, there are many in urban areas that rely on decentralized treatments, whether they have their own treatment systems at home on top of what the city or utility delivers to them. So I would say it's more than 20% of the population.
All right, let's go back to the Water Quality Research Foundation, which has brought you on for a research project on PFAS, and I would love for you to get into that a little bit more and to talk about, first of all, your interest in PFAS and how you got started on this project.
Well, the story of PFAS, of course, is now on top of everybody's mind. at least in North America, but also beyond North America. As part of my research, as I mentioned, we have interest in what we call emerging contaminants and micropollutants. So about 6 or 7 years ago, we came to learn more about PFAS, particularly around, again, those communities that are on well water, but they may not have good advanced treatment systems. So we started to look into how we might be able to treat for PFAS or treat the water for PFAS. Started with one student, and gradually, of course, the scope increased. Now we have a large group of students who are working in this area. So I have been looking at different technologies, different possibilities, and how we might be able to address that. So we've learned more and more about PFAS in the past 6-7 years, and that's how the project with WQRF started.
And what will this scientific project, this research project, attempt to uncover? What are you hoping to learn?
Well, if you look at the technologies that are available for PFAS removal, there are now mostly absorbing technologies, or relying on absorption of PFAS from water. And those are the ones that are approved by the EPA. So EPA has approved granular activated carbon, which is the common adsorbing media for many contaminants. And also there is another type of adsorbent, ion exchange resins. Those are also to some extent approved by EPA. And they work quite well as well. They have their own limitations, and there are some challenges with them. This is only to absorb the PFAS out of the water and generate clean water. Now, if I want to delve into this more, of course, once we remove PFAS from from water using these adsorbents, we are not eliminating the problem. Certainly, we are removing the PFAS from water. The consumers can have clean water, but we are concentrating them into what we say adsorbing media, or these solid phases that need to be dealt later on. Now, as part of our research, we tackled that aspect as well, but this is for now beyond the scope of this particular research with Water Quality Research Foundation. So, to be more specific about what we are going to do as part of this research, is there are many types of adsorbents, means many types of carbons out there. They come from different sources. For example, they come from wood, or they could originate from coconut shells, and so on. So one of the mandates, or one of the objectives we have, are we assess different types of carbon materials to see, to determine the extent of their effectiveness against different types of PFAS. So that's one, basically evaluating different type of carbon adsorbents. The second aspect, which is very important, is that when we talk about PFAS, we're not talking about one compound. We are in fact talking about thousands of compounds that are out there. Now, not all of them are of immediate concern with respect to regulations, and not all of them are present in water at the levels that we can detect. So there are a number of PFAS that are our targets, usually a few dozens. So which one of them we should target? Because if we want to go after all of them, more so in terms of detection, it's going to be extremely costly for any manufacturer or any community for them to monitor for all those, let's say, few dozens of those PFAS, because the analytical parts at such low levels is going to be extremely expensive. So as part of our project, what we are aiming to is to determine which one of those PFAS we can use as surrogate or as representatives for the range of PFAS that we are talking about. So we hope that by the end of it, we can have only a handful of those as a representative of the PFAS that we can monitor. One, in order to see whether we are removing all of the PFAS or all the range of PFAS, and also how effective our adsorbents are against those PFAS. So, for example, if I just go a little bit deeper, if we have a range of PFAS that are, for example, negatively charged, just too simple, it's just those are compounds that are basically within their molecules, they have a negative charge. So they represent a group of PFAS. Now, can we identify from all of these that are negatively charged, one or two of them that can represent all the rest of those in here? And that's what we are hoping that as part of this program, we can identify which one of those can be representatives and whether removing them can assure us and the manufacturers and the homeowners and the communities that we are getting rid of all the rest of the PFAS. So in order to make the water safe, we just need to target those few of those.
That sounds fascinating. Any idea how long this is likely to take? I can imagine right now many of our listeners who are saying, oh, this is fantastic, but we'd love to know right away.
Well, yes. I mean, the answer to any of these questions cannot come soon enough, but certainly it's going to take some time. What we anticipate is that within around 9 to 12 months, basically within the next 1 year time frame, we are able to have the answers to those and be able to present our reports to not only the Water Quality Research Foundation board, but also the memberships. And so hopefully that can be used for their more of a development of the products and technologies, but also assessment of those technologies. As I mentioned, it's very important for the communities or homeowners to be able to know, to be confident that if they're using a particular product, this product is able to remove at least those PFAS that are known to be toxic or harmful and also are regulated.
I don't want to jump the gun here, but it does sound like this has some real value for the point of use and point of entry water treatment community, does it not?
Absolutely. I think that's the intention for this particular research is to make sure that any point of entry or point of use device that is developed can be tested and can be evaluated for their efficiency against the range of representative PFAS that might be targeted. Now, as I mentioned, it's not going to address the entire PFAS issue from the planet because most of these point of entry devices are absorption based technologies, meaning that all we do is just to remove the PFAS from water to bring it into a solid phase. And that solid phase, of course, needs to be taken care of in terms of whether it's a recycling or disposal or anything like that, which we are, as part of my research, we are looking into that as well. But that's outside the scope of this particular research.
Well, when you say that, do you think that there will be a technology down the road at some point that is more than just absorbing the PFAS compounds?
Definitely we need to have other complementary technologies to eliminate the PFAS issue. The real solution at the end of the day will be to destroy them, meaning that to break the carbon-fluorine bond so that we get rid of them altogether, or we eliminate them. But with adsorption, that's not going to be achieved. So what we need to do is to use complementary technologies that we call destruction technologies to be able to eliminate them or defluorinate them. Now, the challenge is that we cannot use those destruction technologies in straight on drinking water, basically taps, or at the point of entry, or for that matter, at a central treatment facility. Because the concentration of the PFAS in water, in our drinking water supplies, are so low. We are talking about nanogram per liters, or parts per trillions, basically. So destruction technologies are not going to be effective, and or they are going to be extremely expensive. So what we do need to do is just first to adsorb them on some kind of a media, and adsorbing media do a great job. Now, the second part will be to take those and now have a concentrated either solid phase, or we bring it back to liquid phase. So we will be dealing with high concentration of PFAS at much lower volume. Under that conditions, we can apply those destruction technologies that, even though they may be very energy intensive, but at least we are dealing with a small volume. And this way we are able to remove the PFAS or eliminate them at much lower cost.
Very interesting, and we're very hopeful that your research is successful so that we can move to a new chapter of success in the battle against PFAS. In the remaining moments here, do you mind if I ask you one of those typical questions, such as, put your crystal ball out in front of you and kind of gaze into the future for us and just answer the question, what's ahead for the water treatment industry?
Well, if I had crystal ball, I would be much better. It would be a much better situation to help out our communities or our population. But I think there are two aspects. Is that one is that we all need to be hopeful that by eliminating these contaminants from the source, from the beginning. So in other words, by not using them, in the case of PFAS, so basically eliminating their use in our consumer products, we are not able to, we won't be needing to talk about their removal from our water. So hopefully that's our future direction, which means that we are not introducing those contaminants into the water in the first place. But I understand that given our lifestyle and our basically how we live and how we function in our society, that may not be all possible, especially with, let's say, climate change and everything that is happening. We will have contaminants. So my hope is that we will have technologies that are going to be efficient and can address multiple problems or multiple contaminants at once. So rather than dealing with individual contaminants and using multiple technologies in order to take one of them off, we will have technologies that will tackle several of these contaminants at the same time.
Very good. Well, let's leave it there. And we so appreciate your joining us, and so appreciate the work that you're doing on behalf of the Water Quality Research Foundation. And we look forward to the results. Maybe we can catch up with you within a few months and get a status update on that. And if you don't mind, that'd be fantastic.
Absolutely, would be happy to do so. And look forward to working on this project and delivering on what the intended objectives are.
Yeah, Dr. Madjid Mohseni, Scientific Director for the Rousseau Center for Mobilizing Innovation at the University of British Columbia. Thanks so much for joining us.
Thank you.